Welcome to Topcast and to my next episode in my discussion of The Fabric of Reality by David Deutsch. We're up to chapter 8, titled The Significance of Life. And this chapter is phenomenal to read if you're one of those people who read the beginning of Infinity first. Because coming back to this earlier work, remember, The Fabric of Reality, 1997, The Beginning of Infinity, some decade later, many people have read The Beginning of Infinity and found the ideas absolutely breathtakingly new. And they are. However, they had antecedents back in The Fabric of Reality. This chapter, perhaps more than most, has it all laid out there on the significance of not merely life, but in particular people and the way in which we can change the cosmos. It's all there. Why wasn't it noticed back then? Well, it was, of course, by some people who happened to be reading the book at that time. But now, these ideas are really beginning to take off. The idea being that life is not some parochial chemical scum. This idea that Stephen Hawking, amongst others, promoted. What did he say? Something to the effect of, we are but a chemical scum covering the Earth, which is just one among a few planets in a solar system, one among many in the galaxy. A galaxy which is one among many trillions, as we know now, throughout the entire universe. So we're not that significant. Chemical scum. Now, as David likes to point out, this is literally true, but it misses the point because there's something special about this set of chemicals. This set of chemicals that we call life. And in particular, this set of chemicals that is living and becomes a person, able to explain the rest of physical reality. There are two questions really being explored in this chapter so far as I can tell. One is, what is the nature of life? What is this stuff called life to begin with? And two, what's the significance of it? Is it fundamental? Given that it emerges from the motion of atoms, basically, how can it be a fundamental feature of the universe? Well, I've already given you one hint. But let's see what David has to say here in The Fabric of Reality. If we want to understand the fabric of reality, after all, the deepest ideas, we need to understand life. Well, do we? Yes, we do. Okay, so let's see what David has to say about this. He begins the chapter with, quote, "From ancient times until about the 19th century, it was taken for granted that some special animating force or factor was required to make the matter in living organisms behave so noticeably different from other matter. This would mean, in effect, that there were two types of matter in the universe, animate matter and inanimate matter, with fundamentally different physical properties. Consider a living organism such as a bear. A photograph of a bear resembles the living bear in some respects. So do other inanimate objects, such as a dead bear, or even in a very limited fashion, the Great Bear constellation. But only animate matter can chase you through the forest as you dodge round trees and catch you and tear you apart. Inanimate things never do anything as purposeful as that, or so the ancients thought. They had, of course, never seen a guided missile," end quote. Or these days, a Boston Dynamics robot. Some people are terrified by, of course. 1997 was a time just before the catastrophists, when it came to artificial intelligence, really gained ascendancy. And they're around us now. It is the zeitgeist. It is what we are swimming in among public intellectuals, that these robots are a sign of the end times. People are terrified of them. They're definitely going to become Terminators, so we're told. Or something like that. We have to really control them. So certainly these things are animated. These Boston Dynamics robots, what people can do with robotics today is absolutely phenomenal. You know, they can dance and they can jump. They're basically as good as people now. You know, you knock them over and they get back up again. You know, some people actually have an emotional reaction to seeing a robot being pushed over, as if the robot can actually suffer or has suffered some indignity of being pushed over. It's just a machine. It's like knocking your toaster over. It's not feeling anything. It's not thinking anything. It can't explain. It's not going to suffer. It doesn't have the relevant senses and relevant ideas. It doesn't have any ideas, except perhaps the ideas of the programmer, which are still the programmer's ideas, not its ideas. It's just following instructions. That aside, the thing isn't living, but why isn't it living? Is it not living because it doesn't have elan vital? It doesn't have the living essence coursing through it? Is that what we have and everything between us and simple cells have? Well, let's read on. David writes, quote, To Aristotle and other ancient philosophers, the most conspicuous feature of animate matter was its ability to initiate motion. They thought that when inanimate matter, such as a rock, has come to rest, it never moves again, unless something kicks it. But animate matter, such as a hibernating bear, can be at rest and then begin to move without being kicked. With the benefit of modern science, we can easily pick holes in these generalizations, and the very idea of initiating motion now seems misconceived. We know that the bear wakes up because of electrochemical processes in its body. These may be initiated by external kicks, such as rising temperature, or by an internal biological clock, which uses slow chemical reactions to keep time. Chemical reactions are nothing more than the motion of atoms, so the bear never is entirely at rest. On the other hand, a uranium nucleus, which is certainly not alive, may remain unchanged for billions of years and then, without any stimulus at all, suddenly and violently disintegrate. So the nominal content of Aristotle's idea is worthless today, but he did get one important thing right, which was most modern thinkers have got wrong. In trying to associate life with a basic physical concept, albeit the wrong one, motion, he recognised that life is a fundamental phenomenon of nature. End quote. And I wonder anyway, if it's about initiating motion, how Aristotle went about explaining something like the melting of ice, let's say. Maybe he didn't see much in ancient Greece, but... But presumably, one moment the ice is solid and not moving anywhere, and the next minute it's flowing. Okay, so this is the beginning of motion, something as mundane as that. But he was trying, of course. Aristotle was a genius. No one else had any better ideas at the time. You've got to start somewhere. And so, hey, good as anything else. But of course, then you've got trees, and trees aren't initiating motion. Or are they? I suppose they're growing. And Aristotle has, of course, said there, life is a fundamental phenomenon of nature. Well, what do we mean by fundamental? Let's see what David has to say, because he goes on to explain this. It's a crucial idea, this, explained to us here in the fabric of reality. It comes up again in the beginning of infinity, and it is still an idea that doesn't seem to have caught on universally. Well, nothing's going to catch on universally, but it hasn't caught on in mainstream academia so far as I can tell. Let's read what David says here. Quote, a phenomenon is fundamental if a sufficiently deep understanding of the world depends on understanding that phenomenon. Opinions differ, of course, about what aspects of the world are worth understanding, and consequently about what is deep or fundamental. Some would say that love is the most fundamental phenomenon in the world. Others believe that when one has learned certain sacred texts by heart, one understands everything that is worth understanding. The understanding that I am talking about is expressed in laws of physics and in principles of logic and philosophy. A deeper understanding is one that has more generality, incorporates more connections between superficially diverse truths, explains more with fewer unexplained assumptions. The most fundamental phenomena are implicated in the explanation of many other phenomena, but are themselves explained only by basic laws and principles. End quote. So this is the idea that what fundamental means is explains a lot more than other things. The deeper you are, the more things you touch. The thing about physics, and why many of us are interested in physics as being fundamental, is because when things change in our understanding of the laws of physics, then things like our understanding of how stars might work can change, how planetary formation might change, our ideas about geophysics could change, some of our ideas about physical chemistry might change, our ideas about computation change, some aspects of mathematics might need to be invented and altered by this. All of these areas are in some way touched by physics. It's got this totalitarian character where it comes to encapsulate other areas. And by that I mean, well, once cosmology was thought to be a domain of religion and theology and spirituality and metaphysics and stuff, something beyond physics. But now, of course, we know there's precision cosmology. You can make measurements and you can have theories that can be tested by observations. It is really becoming a part of physics. Physics begins to incorporate this. Physics begins to incorporate even discussions of biology. You have biophysics and you have constraints placed upon what we know life can do given what goes on in physics. This is why the theories of physics, the laws of physics, are fundamental. They're deep. But then you can talk about Not necessarily just physical ideas. You can talk about moral ideas or economic ideas, or let's say we talk about liberalism, just this idea that people should be allowed to speak freely, okay, this concept of free speech. Now, why? Well, you want to have free speech so you can freely exchange ideas, so you can be more creative. Why should you want that? So you can increase the wealth between people so that they can sell new widgets and so on and so forth. You can't create new stuff if you can't transmit new ideas. You can't advance politically and technologically and scientifically without this deep fundamental idea of the freedom of speech. Freedom of speech is a fundamental idea. It touches lots of other areas. It has an impact on politics and on science and on the growth of technology, on progress more broadly. And so this is why we say this idea is fundamental as well. So something like that has a fundamental effect on many areas. It has a large effect, one might say, politically on nations. But do all fundamental ideas, fundamental concepts, fundamental phenomena have to have huge effects on things? Not necessarily. As David says, quote, not all fundamental phenomena have large physical effects. Gravitation does, and is indeed a fundamental phenomenon. But the direct effects of quantum interference, such as the shadow patterns described in Chapter 2, are not large. It is quite hard to even detect them unambiguously. Nevertheless, we have seen that quantum interference is a fundamental phenomenon. Only by understanding it can we understand the basic fact about physical reality, namely the existence of parallel universes, end quote. Now, of course, today, David has been the one to say and to explain to us that the multiverse is more than just parallel universes. And the universes aren't strictly parallel anyway. They're approximately parallel. They emerge from more fundamental things themselves. Ideas about information and the fungible nature of all physical objects that are within these universes. Universes are classical and emergent. They're approximations to, well, the truly fundamental thing, which is the multiverse, just physical reality as it is. But let's not get sidetracked. We're talking about life here today. And David goes on to talk about the misconceptions that Aristotle had. And interesting as they were, I'm going to skip over that and come to where David is explaining the different conceptions people have about what counts as being fundamental. He talks about how Darwin's theory of evolution, well, it began to explain life, but it's not like it invoked any special kind of physics. It didn't say that there was this new physical law that applied to living things to animate them and not to other stuff. But what did happen in the history of science is that, well, Newtonian physics was just so successful that, well, as David said, it made reductionism attractive. And so he explains this. And so let's read what he says about this. Quote, since faith in revealed truth had been found to be incompatible with rationality, which requires an openness to criticism, many people nevertheless yearned for an ultimate foundation to things in which they could believe. If they did not yet have a reductive theory of everything to believe in, then at least they aspired to one. It was taken for granted that a reductionist hierarchy of sciences, based on subatomic physics, was integral to the scientific worldview. And so it was criticised only by pseudoscientists and others who rebelled against science itself. Thus, by the time I learned biology in school, the status of that subject had changed to the opposite of what Aristotle thought was obvious. Life was not considered to be fundamental at all. The very term nature study, meaning biology, had become an anachronism. Fundamentally, nature was physics. I am oversimplifying only a little if I characterise the prevailing view as follows. Physics had an offshoot, chemistry, which studied the interactions of atoms. Chemistry had an offshoot, organic chemistry, which studied the properties of compounds of the element carbon. Organic chemistry in turn had an offshoot, biology, which studied the chemical processes we call life. Only because we happen to be such a process was this remote offshoot of a fundamental subject interesting to us. Physics, in contrast, was regarded as self-evidently important in its own right because the entire universe, life included, conforms to its principles. End quote. Okay, so this is common knowledge in a way. This is a running joke. In fact, there is even an XKCD cartoon that is quite famous. I'll put it up on the screen. And it has the whole, sequence laid out there, the whole hierarchy of science, if you like. Now, on the far left, for anyone who can't see the screen, you don't need to. On the far left, we have sociologists. And then moving further right, we have the psychologist saying sociology is just applied psychology. And then moving further right, we have a biologist who's saying psychology is just applied biology. Moving further right, we have the chemist saying biology is just applied chemistry. And moving further right, we have physicists saying, which is just applied physics. It's nice to be on top. And then all the way over to the far right is a mathematician who is saying, oh, hey, I didn't see you guys all the way over there. And what's on the x-axis, so to speak, is the label fields arranged by purity. More pure as you move to the right. So mathematics is the most pure or the most fundamental. This is the way it was certainly taught to me. It must have been taught to me because I was quite proud at school of being into physics. And those biology students, well, they were just doing emergent stuff. It wasn't as deep, it wasn't as interesting. There were too many facts to remember. Physics had simple principles. The curious thing was that when I was at school as a high school student, we didn't even learn evolution by natural selection. We just learned what David's about to go through, characteristics of living things and how the taxonomy worked, how you classified things. And I can still remember it to this day. Kingdom, phylum, class, order, family, genus, species. And I'm sort of, what a useless bit of information that's still floating around in my head. I learned that in like year 7 or something. But they didn't teach me the theory of evolution by natural selection. I had to wait until I was an older teenager before I figured out any of that stuff. In fact, I don't think I even was taught it at school. These days, certainly it is taught at school, but I don't think I was taught it at school. So this is, sort of in the 90s. But certainly I was taught the idea that physics is fundamental and, all of chemistry is based on physics and biology just arises out of chemistry and so on it goes. Psychology is just some sort of biology, parochial kind of biology about people. So this is there in our culture. It's still there in our culture, I would say. And David goes on to write, and I had the same experience. He writes, quote, my classmates and I had to learn by heart a number of characteristics of living things. These were merely descriptive. They made little reference to fundamental concepts. Admittedly, locomotion was one of them, an ill-defined echo of the Aristotelian idea. But respiration and excretion were among them as well. There was also reproduction, growth, and the memorably named irritability, which meant that if you kick it, it kicks back. What these supposed characteristics of life lack in elegance and profundity, they do not make up for in accuracy. As Dr. Johnson would tell us, every real object is irritable. On the other hand, viruses do not respire, grow, excrete or move unless kicked, but they are alive. And sterile human beings do not reproduce, yet they are alive too. End quote. As a teacher of this stuff once upon a time, I can tell you that, well, yes, there are acronyms for this kind of thing. Now, I wasn't a biology teacher, but, you teach high school science, and sometimes this stuff crops up. And the acronym, which I never remembered, but it's still taught today, I can guarantee that, certainly in Australian schools, well, actually, around the world, because I have some experience with other curricula. And the acronym is Mrs. Gren. And Mrs. Gren stands for movement, respiration, sensitivity, growth, reproduction, excretion, and nutrition. These are the so-called 7 principles of life, 7 characteristics of life. But I should add a rider to this. Although I was taught this, also back, around about year 7, around about the age of 13, 12, 13, something like that. Today in schools, okay, my most recent schools that I taught in, they did add to this evolution and replication. They do add to this. They concentrate on the more fundamental feature of what life is. And they do talk about DNA. And they even, once you get to like year 10 or something like that, it's transcription and replication. They get into the genes and stuff like that, which is not what I had. It's not what I had in year 10. I think if I had have chosen to do biology in year 11 and 12, they would have taught me this sort of stuff. But I had to wait basically until when I took subjects at university level before I understood this, because taking chemistry and physics in the higher levels of high school, that completely passed me by. I didn't learn about the basics of DNA. Even I knew DNA existed, but I couldn't have told you how any of it worked, so to speak. But I too could have recited the characteristics of life, so-called characteristics of life, as David goes on to say, quote, the reason why both Aristotle's view and that of my school textbooks failed to capture even a good taxonomic description between living and non-living things, let alone anything deeper, is that they both miss the point about what living things are. A mistake more forgivable in Aristotle, because in his day no one knew any better. Modern biology does not try to define life by some characteristic physical attribute or substance, some living essence, with which only animate matter is endowed. We no longer expect there to be any such essence, because we now know that animate matter in the form of living organisms, is not the basis of life. It is merely one of the effects of life. And the basis of life is molecular. It is the fact that there exist molecules which cause certain environments to make copies of those molecules. Such molecules are called replicators. More generally, a replicator is any entity that causes certain environments to copy it. Not all replicators are biological, and not all replicators are molecules. For example, a self-copying computer program, such as a computer virus, is a replicator. A good joke is another replicator, for it causes its listeners to retell it to further listeners. Richard Dawkins has coined the term meme, rhyming with cream, for replicators that are human ideas such as jokes. But all life on Earth is based on replicators that are molecules. These are called genes, and biology is the study of the origin, structure, and operation of genes and their effects on other matter. In most organisms, a gene consists of a sequence of smaller molecules, of which there are 4 different kinds. Joined together in a chain, the names of the component molecules, adenine, cytosine, guanine, and thymine, are usually shortened to A, C, G, and T. The abbreviated chemical name for a chain of any number of A, C, G, and T molecules in any order is DNA. Genes are, in effect, computer programs expressed as sequences of A, C, G, and T, in a standard language called the genetic code, which, with very slight variations, is common to all life on Earth. Some viruses are based on a related type of molecule, RNA, while prions are, in a sense, self-replicating protein molecules. End quote. And David goes on to explain some features of genes, and I think listeners are relatively familiar with this idea that DNA consists of this sequence of genes. It also consists of so-called junk DNA as well. But the genome is the set of all the genes, which code for the building of a particular organism. This is what the genome is. David goes on to explain, after I'm going to skip a little here, and he says, quote, "A gene can function as a replicator only in certain environments, by analogy with an ecological niche, the set of environments in which an organism can survive and reproduce. I shall also use the term niche for the set of all possible environments which a given replicator would cause to make copies of it. The niche, or niche, of an insulin gene includes environments where the gene is located in the nucleus of a cell in the company of certain other genes, and the cell itself is appropriately located within a functioning organism in a habitat suitable for sustaining the organism's life and reproduction. But there are also other environments, such as biotechnology laboratories, in which bacteria are genetically altered so as to incorporate the gene. Those environments are also part of the gene's niche, as are an infinity of other possible environments that are very different from those in which the gene evolved." End quote. Now, David makes some remarks, which I'm going to skip over, about how genes are very finely tuned, so to speak, carefully adapted to their niches. Variations of the gene, even slight variations, will cause them not to get copied in such a way as to enable the organism to thrive. They will cause the death of the organism, or certainly some severe problem anyway. In other words, the gene is adapted to a niche. A replicator is adapted to a niche. And if the replicator changes, if the gene changes even slightly, it's no longer adapted to that particular thing. And so the organism that has that variant is not going to be as successful if it still occupies that same environment, generally speaking. But obviously this kind of implies that there are degrees of adaptation. So you can be more or less adapted. And this is how variation amongst species happens, and therefore you can have differential selection of members of a particular species, and therefore evolution over time. I'm skipping over a fair bit here, and I'm coming up to a part where we get a little hint of constructor theory, just perhaps. So I'll pick it up where David says, quote, "If most variants of the replicator fail to cause most environments of its niche to copy them, then it would follow that our replicator's form is a significant cause of its own copying in that niche, which is what we mean by saying that it is highly adapted to the niche, or niche. On the other hand, if most variants of the replicator would be copied in most of the environments of the niche, then our form of our replicator makes little difference, in that copying would occur anyway. In that case, our replicator makes little causal contribution to its copying and is not highly adapted to that niche. So the degree of adaptation of a replicator depends not only on what that replicator does in its actual environment, but also on what a vast number of other objects, most of which do not exist, would do in a vast number of environments other than the actual one. we have encountered this curious sort of property before. The accuracy of a virtual reality rendering depends not only on the responses the machine actually makes to what the user actually does, but also on responses it does not, in the event, make to things the user does not in fact do. This similarity between living processes and virtual reality is no coincidence, as I shall explain shortly. End quote. Let's just remember the significance of this idea of virtual reality. People like to talk about things like the simulation argument, or just a more prosaic claim that we might be living in a computer in some way, shape or form. The simulation argument being the superset of that. It's a simulation inside a simulation inside a simulation inside a simulation. As if this is somehow explanatory of our circumstance. Of course it's not. If we found we were in a simulation, we'd want to find out what kind of universe the simulation was operating in, or the entire set of simulations, what base reality was like, so to speak. All of that aside, we are already occupying virtual reality. Given that the simulation hypothesis is false on the basis that it's a bad explanation, easily variable and so on, if we just assume normal realism obtains, in other words, physical reality is out there, and we interact with physical reality and come to understand physical reality through our explanations, which we devise to explain our observations. We occupy virtual reality because we're minds, and the minds have only access to physical reality out there beyond your mind via channels of information. Your mind is in complete darkness. It's in your skull, operating on your brain. There's no light there. What's being received is information via optic nerves, via auditory nerves, via the nerves of sensations of other senses. And it's being interpreted. So you are already a computer program of a kind, modelling the rest of physical reality. It's a virtual reality rendering is what you're experiencing of reality. Our explanations themselves, our scientific explanations, are virtual reality of a kind. They are modelling reality that's out there, giving you a more or less accurate picture of what is really going on. And when I say picture, I just don't mean superficial image. It does have that, as David Deutsch says, but more importantly, the mathematical relationships that are involved in explaining something when you write down the explanation in full, as far as we understand it. That is a form of virtual reality. It's not reality itself. It's a model of the reality that we think is going on out there. We know is going on, I should say. These, for me, are synonymous. So what's this got to do with life? Well, let's see what David goes on to say after some more remarks about genes and niches. By the way, my pronunciation of niche or niche, however you like to do it, in Australia we tend to say niche. But I hear other people say niche, so I just get over it. So I guess for the listener, you're just going to have to put up with me switching between these different pronunciations. Sometimes I've got the way I speak in mind, and sometimes I think to myself, what do those British and Americans say? So let's persevere. David goes on to say, quote, "The most important factor determining a gene's niche is usually that the gene's replication depends on the presence of other genes. For example, the replication of a bear's insulin gene depends not only on the presence in the bear's body of all its other genes, but also on the presence in the external environment of genes from other organisms. Bears cannot survive without food, and the genes for manufacturing that food exist only in other organisms. Different types of genes, which need each other's cooperation to replicate, often live together in long DNA chains, the DNA of an organism. An organism is the sort of thing, such as an animal, plant or microbe, which in everyday terms we usually think of as being alive. But it follows from what I have said that alive is at best a courtesy title when applied to the parts of an organism other than its DNA. An organism is not a replicator. It is part of the environment of replicators, usually the most important part after the other genes. The remainder of the environment is the type of habitat that can be occupied by the organism, such as mountaintops or ocean bottoms, and the particular lifestyle within that habitat, such as hunter or filter feeder, which enables the organism to survive for long enough for its genes to be replicated. In everyday parlance, we speak of organisms reproducing themselves. Indeed, this was one of the supposed characteristics of living things. In other words, we think of organisms as replicators, but this is inaccurate. Organisms are not copied during reproduction. Far less do they cause their own copying. They are constructed afresh, according to the blueprints embodied in the parent organism's DNA. End quote. This is clearly obvious when we look at just human beings. You are not an identical copy of your mother and your father. You receive 50% of your genetic material from your father and 50% from your mother. And it is a random 50%. It's not like it's the same 50% because you look different to your brothers and sisters, obviously. And so the selection, which 50% you get from your father and which you get from your mother, is anyone's guess. So we are not direct copies. We have not been replicated. Reproduction is not replication. Replication means copying. And what's the only thing being copied? Some of the genes. Okay, so some random 50% of genes from your father is being copied into your DNA. And the reason why you look different if you're a male and you have a brother from your brothers is because it's a different 50% of the father's DNA that gets copied into you. As David goes on to say, having just said, organisms are not copied. Quote, for example, if the shape of a bear's nose is altered in an accident, it may change the lifestyle of that particular bear, and the bear's chances of surviving to reproduce itself may be affected for better or worse. But the bear with the new shape of nose has no chance of being copied. If it does have offspring, they will have noses of the original shape. But make a change in the corresponding gene. If you do it just after the bear is conceived, you need only change one molecule. And any offspring will not only have noses of the new shape, but copies of the new gene as well. This shows that the shape of each nose is caused by that gene, and not by the shape of any previous nose. So the shape of the bear's nose makes no causal contribution to the shape of the offspring's nose. But the shape of the bear's genes contribute both to their own copying and to the shape of the bear's nose and of its offspring's nose, end quote. So I'll just add a little bit of jargon here for anyone who's interested. The contingent of genes that you have in your DNA is known as the genome. That is the set of all the genes that you have. How they are then expressed, what it goes on to look like as the physical organism that you are, is called the phenotype. So we've got genotype, the set of all the genes in the DNA, and how it's expressed in the environment, what it looks like. That's the phenotype. And Dawkins wrote the book called The Extended Phenotype to explain how the genotype can have effects on the environment. And so, for example, the genes for birds' nests are really in the genome of the bird. Okay? Because everything the bird does, all the behaviours that the bird engages in, are somehow encoded in the DNA. Precisely how, we don't know exactly, but they must be in there, including the things that aren't just in the bird's body. The nest of a bird is not in the bird's body, but it must be there in the DNA in some way, shape or form. Now, we are a bit different. Not all of our manifestations in the physical environment are there encoded in the DNA, not by a long shot. We have something special about our genome. Something in our genome codes for a universal explainer, allowing us to create explanations, understand the world, and bring new knowledge into existence. So this is a unique feature of our genome. Therefore, our extended phenotype, if you like, is a rather strange beast. Possibly the wrong word there. It's a strange phenomena. But whatever the case, when we're talking about bears here and bears' noses, the gene on the genome can be changed. That's a change in the genome. And then when the shape of the bear's nose actually changes, that's a change in the phenotype. And David goes on to say, quote, so an organism is the immediate environment which copies the real replicators, the organism's genes. Traditionally, a bear's nose and its den would have been classified as living and non-living entities respectively. But that distinction is not rooted in any significant difference. The role of the bear's nose is fundamentally no different from that of its den. Neither is a replicator. Though new instances of them are continually being made, both the nose and the den are merely parts of the environment, which the bear's genes manipulate in the course of getting themselves replicated, end quote. You may feel a little uncomfortable with that if you're coming at this for the first time. This idea that organisms, including you, are in some sense just an environment. You are just the environment in which the genes facilitate their own replication. This is the existence of your body is so that these genes can get copied. They're competing to be copied. That's what you are as a matter of life. Now, does this undermine your significance as a living thing? Not at all, because people are not merely their genes. People are minds, and people can create explanatory knowledge. This is what makes us cosmically significant. Now, David will come to this, but just to flag it up ahead. So just in case you're feeling as if, well, you're dismissing the existence of people by saying they're nothing but the environments in which genes are copied. Well, humans are different, as we like to say. But let's keep going. David goes on to say, quote, "This gene-based understanding of life regarding organisms as part of the environment of genes has implicitly been the basis of biology since Darwin, but it was overlooked until at least the 1960s and not fully understood until Richard Dawkins published The Selfish Gene in 1976 and The Extended Phenotype in 1982. End quote. Yes, and I couldn't agree more. These are groundbreaking works. Again, I like to go back sometimes and just recall my university days where, as I say when I'm talking about philosophy on this channel, I was force-fed lots and lots of Wittgenstein and the classics, but no one really taught me Popper. Popper was maybe one or two readings here and there. It wasn't a central focus, even of a philosophy of science program. We just didn't get much of it at all. I also happened to do a subject that was the philosophy of biology, and it was a fascinating subject. It was very interesting. It went all the way through the history of some of this stuff, all the way from the Aristotelian ideas through to the modern day. But when we did get to the modern day, the big guy, the guy that we read lots and lots of, was Stephen Jay Gould. We read lots of Stephen Jay Gould, and the lecturer, the professor that was in charge of the course at the time, was fascinated by his ideas. Now, Gould, from what I remember, I haven't really read much since university from Gould, but he was a proponent of species selection, not the selfish gene idea. These were competing ideas, Richard Dawkins versus Stephen Jay Gould. That was a big debate that went on. Interestingly, Stephen Jay Gould was actually against the use of evolution to explain psychology, in other words, evolutionary psychology. He was against the whole idea. But his ideas were certainly quite interesting. But I mention this because, again, it's another of those cases where I was force-fed his stuff, but I wasn't taught much at all about what Richard Dawkins had said. I think we had, again, a few selected readings from Richard Dawkins. So it wasn't until I'd read The Fabric of Reality that I then read The Selfish Gene and The Extended Phenotype as well. I thought The Extended Phenotype was particularly good. Whatever the case, let's keep going. Let's get into this really important stuff about the importance, the significance of life, where David really comes to the crux of the matter. And he writes, quote, "I now return to the question whether life is a fundamental phenomenon of nature. I have warned against the reductionist assumption that emergent phenomena, such as life, are necessarily less fundamental than microscopic physical ones. Nevertheless, everything I have just been saying about what life is seems to point to its being a mere side effect at the end of a long chain of side effects. For it is not merely the predictions of biology that reduce in principle to those of physics. It is, on the face of it, also the explanations. As I have said, the great explanatory theories of Darwin, in modern versions such as that propounded by Dawkins, and of modern biochemistry, are reductive. Living molecules, genes, are merely molecules obeying the same laws of physics and chemistry as non-living ones. They contain no special substance, nor do they have any special physical attributes. They just happen, in certain environments, to be replicators. The property of being a replicator is highly contextual. That is, it depends on intricate details of the replicator's environment. An entity is a replicator in one environment and not in another. Also, the property of being adapted to a niche does not depend on any simple intrinsic physical attribute that the replicator has at the time, but on effects that it may cause in the future, and under hypothetical circumstances at that, i.e. invariance of the environment. Contextual and hypothetical properties are essentially derivative, so it is hard to see how a phenomenon characterized only by such properties could possibly be a fundamental phenomenon of nature." End quote. Okay, so here David is clearly setting up the argument in its strongest possible terms, only to knock it down. And long-time listeners to Talkcast, and certainly readers of the Beginning of Infinity, will know what's coming next, especially when I read this next short paragraph. You can see how it's all going to be undone, how it's going to have the wind knocked out of it by the conclusion that life is, of course, significant. So what is the argument that life is not significant? Let's keep going. David writes, quote, As for the physical impact of life, the conclusion is the same. The effects of life seem negligibly small. For all we know, the planet Earth is the only place in the universe where life exists. Certainly, we have seen no evidence of its existence elsewhere. So even if it is quite widespread, its effects are too small to be perceptible to us. What we do see beyond the Earth is an active universe, seething with diverse, powerful, but totally inanimate processes. Galaxies revolve, stars condense, shine, flare, explode, and collapse. High-energy particles and electromagnetic and gravitational waves stream in all directions. Whether life is or is not out there among all those titanic processes seems to make no difference. It seems that none of them would be in the slightest way affected if life were present. If the Earth were enveloped in a large solar flare itself, an insignificant event astrophysically, our biosphere would be instantly sterilised. And that catastrophe would have as little effect on the sun as a raindrop has on an erupting volcano. Our biosphere is, in terms of its mass, energy, or any similar astrophysical measure of significance, a negligible fraction even of the Earth. Yet it is a truism of astronomy that the solar system consists essentially of the Sun and Jupiter. Everything else, including the Earth, is just impurities. Moreover, the solar system is a negligible component of our galaxy, the Milky Way, which is itself unremarkable among the many in the known universe. So it seems that, as Stephen Hawking put it, the human race is just a chemical scum on a moderate-sized planet orbiting round a very average star in the outer suburb of one among 100 billion galaxies. End quote. And of course, we have continued to revise up our estimates of the number of galaxies in the universe. It went to 200 billion, then it went to 1 trillion, and now I think it stands at 2 trillion in the observable universe. Never mind the rest of the universe, which might go on forever. So these numbers just keep getting larger. And therefore, by this argument, we keep getting more insignificant. David goes on, quote, "Thus the prevailing view today is that life, far from being central, either geometrically, theoretically, or practically, is of almost inconceivable insignificance. Biology in this picture is a subject with the same status as geography. Knowing the layout of the city of Oxford is important to those of us who live there, but unimportant to those who never visit Oxford. Similarly, it seems that life is a property of the same parochial area, or perhaps areas of the universe, fundamental to us because we are alive, but not at all fundamental, either theoretically or practically in the larger scheme of things. But, remarkably, this appearance is misleading. It is simply not true that life is insignificant in its physical effects, nor is it theoretically derivative. As a first step to explaining this, let me explain my earlier remark that life is a form of virtual reality generation. I have used the word computers for the mechanisms that execute gene programs inside living cells, but that is slightly loose terminology. Compared with the general purpose computers that we manufacture artificially, they do more in some respects and less in others. One could not easily program them to do word processing or to factorize large numbers. On the other hand, they exert exquisitely accurate interactive control over the responses of a complex environment, the organism, to everything that may happen to it. And this control is directed towards causing the environment to act back upon the genes in a specific way, namely to replicate them, such that the net effect on the genes is as independent as possible of what may be happening outside. This is more than just computing, it is virtual reality rendering. The analogy with the human technology of virtual reality is not perfect. First, although genes are enveloped, just as the user of virtual reality is, in an environment whose detailed constitution and behaviour are specified by a program, which the genes themselves embody, the genes do not experience that environment because they have neither senses nor experiences. So if an organism is a virtual reality rendering specified by its genes, it is a rendering without an audience. Second, the organism is not only being rendered, it is being manufactured. It is not a matter of fooling the gene into believing that there is an organism out there. The organism really is out there. However, these differences are unimportant. As I have said, all virtual reality rendering physically manufactures the rendered environment. The inside of any virtual reality generator, in the act of rendering, is precisely a real physical environment, manufactured to have the properties specified in the program. It is just that we users sometimes choose to interpret it as a different environment, which happens to feel the same. As for the absence of a user, let us consider explicitly what the role of the user of virtual reality is. First, it is to kick the rendered environment and to be kicked back in return. In other words, to interact with the environment in an autonomous way. In the biological case, that role is performed by the external habitat. Second, it is to provide the intention behind the rendering. That is to say, it makes little sense to speak of a particular situation as being a virtual reality rendering if there is no concept of the rendering being accurate or inaccurate. I have said that the accuracy of a rendering is the closeness as perceived by the user of the rendered environment to the intended one. But what does accuracy mean for a rendering which no one intended and no one perceives? It means the degree of adaptation of the genes to their niche. We can infer the intention of genes to render an environment that will replicate them from Darwin's theory of evolution. Genes become extinct if they do not enact that intention as efficiently or resolutely as other competing genes. So living processes and virtual reality renderings are, superficial differences aside, the same sort of process. Both involve the physical embodying of general theories about an environment. In both cases, these theories are used to realise that environment and to control interactively not just its instantaneous appearance, but also its detailed response to general stimuli. End quote. And we're about to come to a very beginning of infinity style claim about all of this, but you can guess where this is going. It's saying here, David is saying here, that the organism is a virtual reality rendering specified by its genes. It's embodying a theory about the environment so that the genes can get replicated. Embodying a theory about the environment. What does that mean? Well, David says it in the very next sentence. Let me quote it. He says, quote, genes embody knowledge about their niches. Say it again. Genes embody knowledge about their niches. This here is the beginning of infinity claim that we have two kinds of knowledge that exist in the universe that we know about so far. We have explanatory knowledge. This is the stuff that people are constructing in order to explain the universe around them. This is our scientific knowledge and so on and so forth. That arises via conjecture and refutation of ideas. This is the stuff designed by people, intelligently designed by people. It's also the stuff that tends to get itself copied because it's so useful, it solves a problem and all of that stuff as well. This, genes embody knowledge about the niches, this is the biological, evolutionary kind of knowledge. In both cases, ultimately, at the heart of both of them, is this method of conjecture and criticism, but we don't really know how it is that the knowledge is created. We just know it has something to do with this process. So let me read what David has to say about this, and we'll call it a day there. He says, going back, quote, genes embody knowledge about their niches. Everything of fundamental significance about the phenomenon of life depends on this property, and not on replication per se. So we can now take the discussion beyond replicators. In principle, one could imagine a species whose genes were unable to replicate, but instead they were adapted to keep their physical form unchanged by continual self-maintenance and by protecting themselves from external influences. Such a species is unlikely to evolve naturally, but it might be constructed artificially. Just as the degree of adaptation of a replicator is defined as the degree to which it contributes causally to its own replication, we can define the degree of adaptation of these non-replicating genes as the degree to which they contribute to their own survival in a particular form. End quote. Just pausing there. That's brilliant. This is the idea of knowledge that once instantiated in a physical substrate tends to cause itself to remain so. It is the thing that tends to get itself copied. There it is in black and white all the way back in Fabric of Reality. The degree of adaptation of a replicator is defined as the degree to which it contributes causally to its own replication. David goes on, quote, consider a species whose genes were patterns etched in a diamond. An ordinary diamond with a haphazard shape might survive for eons under a wide range of circumstances, but that shape is not adapted for survival, because a differently shaped diamond would also survive under similar circumstances. But if the diamond-encoded genes of our hypothetical species caused the organism to behave in a way which, for instance, protected the diamond's etched surface from corrosion in a hostile environment, or defended it against other organisms that would try to etch different information into it, or against thieves who would cut and polish it into a gemstone, then it would contain genuine adaptations for survival in those environments. Incidentally, a gemstone does have a degree of adaptation for survival in the environment of present-day Earth. Humans seek out uncut diamonds and change their shapes to those of gemstones, but they seek out those gemstones and preserve their shape. So in this environment, the shape of the gemstone contributes causally to its own survival, end quote. So there we have the notion of resilient information. Okay, resilient information. This Chiara Marletto uses this in the Science of Canon Kant. Another explanation of what knowledge is, another way of coming up with what knowledge is, which captures this idea that If you've got a diamond, one of the most resilient of all substances out there naturally occurring, which had information encoded in it which caused it to be able to keep thieves away, to stop other information being put onto it, to prevent its own corrosion and so on and so forth, its own erosion, well, then you have something interesting, something alive. So David goes on to say about these diamond-type species, quote, when the manufacture of these artificial organisms ceased, the number of instances of each non-replicating gene could never again increase. But nor would it decrease, so long as the knowledge it contained was sufficient for it to enact its survival strategy in the niche it occupied. Eventually, a sufficiently large change in habitat or attrition caused by accidents might wipe out the species, but it might well survive for as long as many are naturally occurring species. The genes of such species share all the properties of real genes except replication. In particular, they embody the knowledge necessary to render their organisms in just the way real genes do. It is the survival of knowledge, and not necessarily of the gene or any other physical object, that is the common factor between replicating and non-replicating genes. So strictly speaking, it is a piece of knowledge rather than a physical object that is or is not adapted to a certain niche. If it is adapted, then it has the property that once it is embodied in that niche, it will tend to remain so. With a replicator, the physical material that embodies it keeps changing, a new copy being assembled out of non-replicating components every time replication occurs. Non-replicating knowledge may also be sufficiently embodied in different physical forms, as for example when a vintage sound recording is transferred from a vinyl record to a magnetic tape and later to a compact disc. One could imagine another artificial non-replicator-based living organism that did the same sort of thing, taking every opportunity to recopy the knowledge in its genes onto the safest medium available. Perhaps one day our descendants will do that. End quote. And that's where I'll end the reading for today. But there, we end it with what's in the beginning of infinity. And now it's amazing because I read this, I don't know how many times I've read this book, but it's one of those things where I didn't really get that on the first reading of The Fabric of Reality. This idea that it's all there, here in this chapter 8, The Significance of Life. This idea that knowledge is substrate independent. So he's not using the word substrate there, but he's saying the knowledge can exist in different physical forms, but it's still the same knowledge. And when we're talking about the evolution of life, where we're saying that it's the genes that are getting copied, really what we mean? It's not the physical molecules, it is the knowledge that those molecules represent. The knowledge is an abstract thing. In theory, of course, you could, in a laboratory, read out the entire genome, read out the set of genes in an organism, print it out on a piece of paper, and there it is on the piece of paper, and then recapitulate it into a new genome. So you've transmitted, not via a biological process, but some other process. Call it what you like. However you go about reading and then printing out stuff and then taking the printout and using that in the laboratory to reconstruct the organism. That is taking biological knowledge from one place to another through a different physical media. The knowledge is substrate independent. Substrate independent means it doesn't depend on whatever physical instantiation it has, whatever physical form it has. It's the knowledge, the useful information that's being copied. Both when we're talking about evolution by natural selection, the useful information is being copied so that the genes can survive via a method of reproduction that goes on between organisms but causes the replication of genes, but it's the knowledge that's being copied. That's what's going on with evolution. It's being copied because it's useful. The genes are useful. Useful to what? Useful to themselves, okay? Useful to their own survival and propagation throughout the environment. So we still haven't quite got, admittedly, to the significance of life. The significance of life cosmologically speaking, but you can see it's being set up, and we already know, here at Talkcast, we already know that this process that is life is something that can cause vast changes to whole planets. And ultimately, of course, once it is able to transform the surface of a planet in the form of us, human beings, then it can move out into solar systems, galaxies, and the rest of the universe. It can be as significant as what gravity is on the way in which the universe appears on large scales, over large time frames and over large regions of space. If we could have the God's eye view of the multiverse, we would see that it is knowledge, the flow of information, that is what is really the big structure in the universe, that what shapes the multiverse as a whole. We're not quite there yet. It's coming. but we already have the background knowledge to predict where it is coming from. And next time, we'll get down into the nitty-gritty, into the details of the remainder of this chapter. But until then, bye-bye.